Everyone. I hope you're all doing well today. We're going to continue our discussion on acids and bases. So in particular, we're going to cover indicators. So previously we saw that solutions can be acidic, neutral, or basic. And we saw that we can use something called a pH to determine how acidic or basic a solution is. So remember, pH ranges from 0 up to 14. So right in the middle is the value 7. And if something has a pH of 7, it is neutral. So that would be something like water. But if something has a pH between 0 and 7, it is considered acidic. And then if a solution has a pH between 7 and 14, it's considered basic. Now, sometimes we'll add room for error, right? So water naturally has some ions floating around in it. And in particular, things like fluoride ions are added to water to help with the health of your teeth, for instance. Now, some of these ions can cause water to be a little acidic or a little basic. It just depends on the concentration of those ions. So if you measure the pH of water, sometimes it's a little below 7 or a little above 7, but that's okay. It's generally neutral. So there is some wiggle room with these definitions. Now also remember, pH is dependent on the concentration of hydrogen ions in solution. Or we could also say it's dependent on hydronium ions. So remember, hydronium is H3O+, and that is equivalent to H+. Now up above, you can see some pH values, and they're ranging from 2 up to 12. And these are different indicators up above. So we have one type of indicator at the top, one in the middle, and one at the bottom. So indicators change color with changes in pH. So the indicator on the very top row, that is pink in acidic solutions and kind of yellow in basic solutions. And then the indicator in the middle is yellow in acidic conditions and blue in basic conditions. And then in the last row, this indicator is clear in acidic solutions and pink kind of around neutral solutions, and then it turns red in basic solutions. So these are different indicators that we could use to detect if something is acidic or basic. Another way that we can test the pH of a solution is using something called pH paper. So pH paper changes color based on the pH of solution. So you'll notice that for a pH of 1, pH paper is a reddish color. And then as we see an increase in pH, so we're going towards a basic solution, the color changes from orange to yellow to green to blue to really dark purple. So under acidic solutions or acidic conditions, we have a range of red to orange to yellow. And then at a neutral pH, this paper is green, kind of a light green. And then under basic conditions or in basic solutions, pH paper is either dark green, dark blue, or dark purple. Now, this isn't super exact. So for instance, if you get a bluish color on your pH paper, you might say, well, the pH is within a range of 9 to 10. But you're not going to get a super specific answer. So pH paper is great if you just need a general idea of the acidity or basicity of a solution, but there are other techniques we can use to get an exact value. Now, other types of pH paper are red and blue litmus paper. So red litmus paper turns blue in a base, and it remains red in acids. So that's another way that you can just get a general idea of whether something is an acid or a base. But again, this won't tell you any specific pH values. Blue litmus paper, on the other hand, will turn red in an acid and remain blue in base. So again, not super specific, it's just kind of giving us a general idea of acidity or basicity. Another indicator we can use is cabbage juice. So if you smash up a bunch of cabbage leaves and then isolate the liquid, you can use that to determine if a solution is acidic or basic. So you can just add a couple drops of the cabbage juice to your solution. And if you have a really acidic solution with a pH of about 2, the cabbage juice will turn the solution a reddish pink color. And that's true for most acidic solutions. And then once we start getting into neutral territory, the cabbage juice will turn sort of a bluish color, kind of a blue-purple, I guess. And then once you start getting into more basic solutions, the cabbage juice will turn the solution a sort of bluish green or yellow color. So on the left we have acidic solutions, on the right we have basic solutions. So that's kind of cool that cabbage juice can do that. So another more specific way to analyze acids and bases is to use something called a titration technique. So if we're analyzing an acid solution, typically we're trying to determine the amount of acid in the solution. So instead of just using pH paper or cabbage juice as an indicator, we can get a more exact amount of acid in solution, or a more exact pH, for instance. All right, so in a titration, we're going to have typically an acid with unknown concentration. So for instance, maybe in that flask we put 25 milliliters of unknown concentration of hydrochloric acid, for example. So we would add that using a pipette. So this is a volumetric pipette that's shown in the figure. And volumetric pipettes are very accurate. So they have a calibration mark on the top stem, and that's where we typically try to aim our liquid towards when we're using a pipette. All right, so then in the next step, we're going to add a few drops of indicator solution to the Erlenmeyer flask. So the indicator will change color based on pH. So we can get an idea of how acidic or basic the solution is. And initially, of course, it's acid, so it's going to be very acidic. All right, so we add some indicator. And there's a lot of different types of indicators we could use. So maybe we use cabbage juice. We'll actually talk about a very specific indicator called phenolphthalein, and that is the most commonly used indicator in titrations. Okay, So once we've added our indicator, then we're going to add a solution of base. And that solution has a known concentration. So we'll add a basic solution of known concentration. And the way we're going to deliver that solution is using something called a burette. So a burette is a really long, almost kind of looks like a graduated cylinder, but at the very bottom, instead of a sturdy base, we have a valve or stopcock that is going to deliver solution to our acid. So when the stopcock is horizontal, the burette is closed and solution won't leak out. But then when the stopcock is vertical, then solution is released. All right, so then what we're really doing here is performing a neutralization reaction. So for instance, if we're using hydrochloric acid and sodium hydroxide, we're going to end up with NaCl and H2O, just like we've seen previously. So our original solution in the flask is acidic, and our original solution in the burette is basic, but at a certain point, they're going to completely neutralize each other once we've added enough base. So the point at which all of the acid has reacted is shown by a color change in the indicator, and that's known as the end point of the titration. So, for instance, cabbage juice we saw is pink in acidic solution, and then when it's neutral, it's sort of a bluish purple color. So if the indicator, let's say, was cabbage juice, once all of the base reacted with all of the acid, we would have a greenish color. And that's how we would know to stop the reaction, because we see that it's neutral, so all of the acid has reacted. Now the other thing we do is we read the volume in the burette before and after adding base. And then we take the difference to figure out how much base we actually added to our acid. So the concentration of the base and the volume that we added allows us to determine the concentration of acid. So really, again, the whole point of a titration is to figure out what is the concentration of acid, or how much acid do we actually have in solution. And we'll do some example calculations so you can kind of see how this information is useful. So I mentioned that the most common indicator used for titrations is something called phenolphthalein. It's a really long, complex name. I have trouble spelling it sometimes. But you'll notice that down below we have 3 different figures. And in figure 1, we have our acid in the flask. And then up above is the burette containing base. So initially, before we add any base, the acid is clear. And we have added the phenolphthalein, which I'm just going to write as indicator. But then, once we start adding base, then we notice the solution turning kind of pink. And if we give the flask a good swirl, that pink color might disappear. So what we're really looking for is for the pink color to stay for about 10 seconds total. So when that occurs, that is the end point. So that means that all acid has reacted. So phenolphthalein is a super useful indicator because it is clear under acidic conditions and then pink under basic conditions. So if this is our pH scale at the top, again, between 0 and 7 for pH, phenolphthalein is clear. And then as soon as we hit that neutral point or a little bit above it, the phenolphthalein turns pink. So under basic conditions, phenolphthalein is pink. And that's how we know we've reached the neutral point of our reaction. So if none of that made sense, here's a video. Hopefully this will help to show what happens during a titration. So let's open up YouTube.
Imagine if you could design products as quickly as your ideas flow. Imagine if...
All right. Okay, so hopefully that helped you visualize how to perform a titration. Again, we have acid in the flask that's below the burette, and we have base in the burette. And again, the base had a known concentration, and then we added a certain volume of base to neutralize the acid. And then we knew that the acid was neutral because the indicator changed color. So, one last type of pH measurement that we can perform is using a pH meter or electrode. So this is probably the most accurate way to get a pH reading. So off to the side in the first figure, you'll notice kind of a little stick thing in the flask. That's called a pH electrode or pH meter. And on the bottom of that pH meter is a small glass bulb, and that bulb can read how much or how many ions are in solution. And then it can turn that into a pH value. So on the device off to the left there, initially this acid has a pH of 3.03, so that is super specific. And then maybe we perform a titration and determine the pH of our solution as we titrate. So partway through the titration, after we've added a little bit of base, we notice that the pH of the solution has increased to 4.76. So it's becoming less acidic, becoming more basic. And then at the end of the titration, we have a pH of 8.76. So that's sort of neutral, maybe a little bit basic. So we can try to find that end point using a pH meter instead of an indicator. So that's also possible. Now, these electrodes are really fragile and somewhat expensive. So, they're not used quite as often, especially if you don't need an exact pH value, but just a general pH value. I used to use one of these electrodes in my lab when I was doing research because we needed our samples to have the same exact pH as human blood. And human blood has a pH of 7.4, approximately. 7.4. So we needed our solutions to have that same pH, so we always had to double check, but we needed something that was super specific, so we always used an electrode. But for other scenarios, you might not have to be exact. All right, so let's go through how to utilize the information from a titration. How do we calculate how many hydrogen ions are in an acid solution? So again, in a titration, the concentration of the acid is usually unknown, but the concentration of the base in the burette is usually known. Now, you could flip these two if you wanted. You could have the acid in the burette and the base in the flask. That's totally fine, but most often we have the acid in the flask and the base in the burette. All right, so we said that during the titration, we add some base to our acid until we reach the end point, so the point at which it's neutral. And then we record the volume of base added. So we can use the volume of the base and its concentration to determine how many moles of base were added. So here is our calculation for that. So if we take our volume, and we will need it to be in liters, we can then multiply that by the molarity concentration, which is in moles per liter. Liters will cancel, and we'll end up with moles of the base. Now, remember at the end point, that's when all of the acid has reacted. So what we can conclude is that the moles of the base are equivalent to however many moles of acid are in the flask. So sometimes, though, the ratio of acid to base is 2 to 1 or 1 to 2, so we do have to take that into account. But once the moles of base have completely reacted with acid at the end point, we can convert moles of base to moles of acid using stoichiometry, so the ratios between them. Then we can use the moles of acid that we determined and the original volume of acid that we had at the beginning to find the concentration of the acid. So the molarity of the acid is equal to moles of acid over liters of acid. And then we have our unknown concentration, so it's solved. So let's actually put all this into an example and see how this works. So let's say a chemist performs a titration between 0.1 molar NaOH and 25 milliliters of hydrochloric acid with unknown concentration. The end point occurs after 30.2 milliliters of base is added to the acid. What is the concentration of the acid? So let's write out what we're given. So you can see we're given the reaction equation up above. So that's great. We can then use the ratio between acid and base. But we're also given that we have a 0.1 mole per liter solution of NaOH. So I'm just taking that capital M and writing out the full units of moles per liter. We're also told that we added 30.2 milliliters of NaOH to our acid. Now, from that information, remember, we can calculate how many moles of base that we added to our acid. So volume times molarity is equal to moles. Then we were also told that we have 25 milliliters of hydrochloric acid, but we don't know its concentration yet. So that's what we're trying to solve for. So what we need is the molarity of HCl, so the moles per liter. Now we already have the volume, it's 25 milliliters, but we don't know how many moles of HCl we have. So really what we're trying to find are moles of HCl. So then our plan, so let's write this on a separate slide. Our plan is 1, find moles of NaOH. 2, find moles of acid, so HCl. And then 3, find the concentration of acid. Okay, so let's go through each of those steps. So first, let's find the moles of NaOH that were added to the acid. Okay, so 1, we're going to multiply the volume by the concentration of the base. However, we were given a volume in milliliters, so we have to convert that to liters first so that our units cancel correctly. Okay, so let's convert milliliters to liters. How many milliliters are in 1 liter? 1,000. Okay, so when we plug that in to our calculators, we get 0.0302 liters of NaOH solution. So now we can use that volume and our concentration of NaOH, which was 0.1 moles per liter, to tell us how many moles of sodium hydroxide or base we added to the acid to reach the end point. So 0.0302 times 0.1 will give us 0.00302 moles of NaOH. So remember to always double check that your units cancel. So milliliters of NaOH cancel with milliliters. And then in our second calculation, liters of NaOH cancel with liters. Perfect. Okay. So now in step 2, let's use our ratio of acid to base in our equation above to determine how many moles of acid we had in our flask. Because if we know the ratio, then we can figure out the moles. So we already said that we have 0.00302 moles of NaOH that reacted with acid. And from our equation up above, we can see that they react in a 1-to-1 ratio. So we'll just put 1 mole of HCl, because we want moles of HCl, in the numerator. And then in the denominator, we will put 1 mole of NaOH. All right, so super easy. Because base and acid react in a 1-to-1 ratio, we have the same number of moles of acid. Now that's not always true. Again, sometimes ratios might be 2-to-1, 1-to-2, etc. But in this case, it was super easy. All right, so the last step. Now that we have moles of HCl, we were already given milliliters, so the volume of HCl solution. So all we have to do is calculate moles per liter, our molarity concentration. But again, we were given milliliters, so we need to convert that to liters first. Okay, so we had 25 milliliters of our HCl solution, and we'll just do our liter conversion here. So 25 divided by 1,000 gives us 0.025 liters of hydrochloric acid solution. And now we can calculate molarity. So molarity is equal to moles per liter. So we already said that we have 0.00302 moles of HCl. And we have the volume in liters. So that was 0.025 liters of HCl. All right, so 0.00302 divided by 0.025 should give us 0.12 moles per liter of HCl. Okay, so we found out the concentration of the acid. So what we could do is use that concentration to determine a pH value. So we know that HCl, when it's added to water, just ionizes into hydrogen ions and chloride ions. So that tells us that the concentration of HCl is equal to the concentration of the hydrogen ions, because everything just dissociates. So then we could use the concentration there, plug it into our pH equation, and get the pH of the solution. So that's another option too. All right, let's do another practice problem. This one will be a little more challenging, so we'll kind of stretch our brains a little bit here. Oh, and this is the solution slide if you want to look that over later. So our second example, a chemist has an unknown solid acid. So they don't know what this acid is. They can identify the acid by determining its molar mass in grams per mole. The solid acid weighs 0.095 grams. They then dissolve the acid in water and titrate it with 0.1 molar NaOH. The end point is reached after addition of 15 milliliters of NaOH solution. So we have a few given values here. All right, so this chemist is trying to figure out what is this acid that I have. I have no clue what it is, but if I perform a titration, I can figure out how many moles of acid I have, and I already have the mass, 0.095 grams, so I can calculate the molar mass of this acid and then look up different molar masses for different acids and match it to one of those. All right, so let's write what we're given. So we're told that we have a 0.1 molar solution of sodium hydroxide, and that's pretty standard for titration, so you'll probably see that concentration a lot. And then we're told that the end point is reached after adding 15 milliliters of that solution. So we also have the volume, and remember that will give us moles of NaOH. All right, so then we're also told that the mass of the acid is 0.095 grams. And what we need to find is the molar mass of the acid. All right, so our plan here, first, let's find the moles of the base, because then we can relate that to moles of acid. And then third, we're going to find the molar mass of the acid. Okay, so let's go through each of those steps. All right, so one, we're going to find the moles of NaOH. So remember, if we multiply volume by concentration, that will give us moles, but we need the volume units to match. So we have to convert 15 milliliters to liters. All right, so we'll do this conversion. So 15 divided by 1,000 will give us 0.015 of the NaOH solution. So now we can use that and multiply it by our concentration of NaOH to find the moles of NaOH. So we have 0.1 moles per liter. All right, so 0.015 times 0.1 gives us 0.0015 moles of NaOH. Now, let's assume that the base and the acid react in a 1-to-1 ratio. So for step 2, we're making a bit of an assumption here. So let's assume that 1 mole of acid reacts with 1 mole of NaOH. So that means we have the same number of moles of acid. Okay. Now in the last step, we're going to take that number of moles and use it to solve for molar mass, so grams per mole. All right, so we've got our mass. So remember, molar mass is grams per mole. So we're going to take the mass that we saw earlier and then divide that by the moles that we calculated, which was 0.0015. All right, so 0.095 divided by 0.0015 gives us 63 grams per mole. Now, if we looked up in a table the molar masses of different acids, the one that this most closely matches is nitric acid. So HNO3 has a molar mass of 63 grams per mole. So we can probably conclude that this acid is HNO3. Now, a true chemist would do another experiment just to verify that this is the result that he expected. However, this is a good start. All right, so here's the solution slide if you want to reference that later. And we'll stop there today. Next time, we'll talk about something called a buffer. Buffers are a special type of solution that can maintain a certain pH level. No matter if you add acid or base to it, it will stay at the same pH. So we'll talk about that next time. I will see you then.